We are continuing the next part of this unit, third of the paper 2, X-rays. In 1895 by Röntgen, we discover this particular X-rays. And what is the X-rays that you should know? All you are familiar with this X-rays. Emission of the very penetrating rays from the cathode ray tube, he called it as a X-ray. X-ray were found to be produced whenever the fast moving electrons strike a target, and the scientist Röntgen found that X-rays had the very great penetrating power. It was also found that X-rays could blacken a photographic plate and could ionize a gas. X-ray travel in a straight line from the source and were not affected in passing through electric or magnetic field. They were thus not charged particle. Hence, he concluded that X-rays are electromagnetic radiations of exactly same nature as visible light of extremely short wavelength. That you have to remember. That wavelength is again 100 to 0.0001 angstrom. Production of the X-rays. Coolidge tube is used. Coolidge tube is X-ray is produced by the Coolidge tube, that we have to remember. Just for this, we are not going in detail of this particularly. Let's see, this is the Coolidge tube that is used for the production of the X-rays. Continuous and the characteristics of the X-ray spectra. A Coolidge gives the Coolidge tube gives the X-ray spectra. That crystal spectrometer is used to resolve this particular spectra, and X-rays emitted by the target of the X-ray tube is found to be considered two distinct types of the spectra. One is the continuous spectrum and second one is the line spectrum that superpose on the continuous spectrum. Here the spectra has been shown. Lambda max, which is found to be shifted to shorter wavelengths with increase in voltage. What are the main features of this curve? Intensity increases, increasing the potential difference across the tube. For a given potential difference, the curve from the longer wavelength reaches a maximum and then falls up rapidly to zero with a sharp out of wavelength lambda minimum. The intensity is increased higher. Here it is origin of continuous spectrum. Most of the electrons in the Coolidge tube undergo the glancing collision with the atoms of the target material and lose their energy. Some of the electrons are stopped suddenly upon hitting a target. These electrons are rapidly decelerated. Continuous spectrum results from the radiation emitted by the electrons when they are deaccelerated or accelerated in the control field of the force of the nuclei of the target atom. The term Bremsstrahlung or braking radiation is used to describe the radiation emitted by the charged particle when deaccelerated in this manner. And there is a defined short wavelength limit lambda minimum to continuous X-ray spectrum, which is independent of the material of the target. This short wavelength limit is obtained by the Dunen and Hunt's law. Dunen and Hunt's law is when the voltage across the tube is increased, the wavelength limit lambda minimum is shifted towards the smaller value. This can be understood on the basis of the quantum concept of the radiation. Thus, Dunen and Hunt's show the short wavelength limit continuous spectrum varies inversely as the voltage applied across the tube. If an electron accelerated through the potential difference V volts, EV is equal to h nu max, then you will get the lambda minimum is equal to this particular value is there. This is called as the Dunen-Hunt's law. Origin of characteristics line spectrum. Then this is not again we are directly diffraction of the X-rays. The wave nature of the X-rays is established only by the diffraction and interference experiment. That when Loy noted that the close order array of the atoms layer is by the layer in the natural crystal could act as a diffraction grating for the X-rays. That we are not again going in detail of such a thing. Bragg's law. Bragg's law we will see. What is Bragg's law? That is 2d sin theta is equal to n lambda is called as the Bragg's law. It gives the relationship between Bragg's law gives the relationship between the angle of refraction sin that theta with the wavelength. 2d sin theta is equal to n lambda. That d is nothing but the phase difference is there. or so you can call it as a path difference. The Bragg's X-ray spectrometer is used to study this particular Bragg's law. Determination of the interplanar spacing D value you can determine here. Properties of X-ray we will see. X-ray electromagnetic radiation of the short wavelength. X-rays are highly penetrating and can pass through many solids. X-ray ionize the gas through which they pass. X-ray affect phototropic light. X-ray produce fluorescence in the fluorescent material like the zinc sulfide and tungsten, barium, platinum cyanide. X-ray propagate in the straight line with the velocity of light. Application of the X-rays in the field of the medical science, radiotherapy, industry, engineering, detective departments, and research. You can see there are so many applications of this particular X-rays are there that can be used in the various field. You can we are doing the X-rays of any part of our body. Then in the compound tomography, that is a CT scan, where is also the X-ray is used. That are they are also the X-rays. Radiotherapy is done by this particular X-rays. In the industry, this particular X-rays are used. You go with this particular part. Here are the numericals are in based on this particular wavelength of X-rays. We will see the MCQs. These are the unsolved numericals. Okay. When the voltage across the Coolidge tube is increased, the wavelength limit of the produced X-rays is shifted towards the smaller B value. Okay. 2D sin theta is equal to n lambda is Bragg's law. In continuous spectrum superimposed with the spectrum of the X-rays, the intensity of dot width increases with PD across the intensity increases with the increase in the potential difference. Okay. That then law pattern is obtained due to diffraction of the X-rays at a lattice point. Okay, here we will stop. Thank you.